Okay, so this is the second day of problem solving. One of the things that I'm thinking of doing, if you guys are interested, is giving you the option of just starting different classes with a problem you find interesting, a problem you've looked at, just so that we look at it live and I do not have things pre-prepared, so that you can actually see the thought process. Now the problem is, of course, anything I look at ahead of time, I can try to not look at it too deeply, but there is, of course, the advantage that I'm looking at it and it's not live. And it's valuable to just see how you would approach something. So I wanted to just start today with, I will challenge myself. And so I have not spent too much time thinking about this, but I've spent 2 to 3 decades doing problems like this. And so doing that many problems, you have a rough idea of how to attack. So consider A, B, and C are greater than 0. Prove A plus B times B plus C times C plus A is greater than or equal to 8A, B, C. I'm not sure how much of this we'll do today. We will eventually move and do an entire unit on inequalities. This is one of the standard things in problem-solving classes. But I thought it would be worthwhile to just look at something like this and just talk, how would you approach something like this? So you're seeing it fresh. I'm deliberately not giving you something that you were supposed to have been reading for today. Today's topic is supposed to be mathematical induction. Maybe we could induct by having what? How could we try to do induction on this? So that's more trying to use continuity. So induction, we have to say, we prove it for a certain case, and then we move on to the next case. So it would be a little bit hard to do this by induction, but I do see one way to try to do it by induction. Maybe on the number of variables, right? This could be the case where we have 3 variables. Maybe there's a version when there's 2 variables. Maybe there's a version when there's 1 variable. Maybe there's a version when there's n variables. This is similar to the Queen's problem we did. Can you look at something and can you extract what's going on? And if so, how do you view 8? So how would you view 8? Yes?
2 to the n, where n.
Ah, so maybe this is 2 cubed or 2 to the n in general. Let's try to write a better 3 for the people at home. And that could actually give you some insights as to how to attack this problem. Is that maybe this 8 is coming from 2 cubed. Maybe not, but just thought processes how to attack something like this. What's the first thing you notice when you look at this? So what do you see when you see something like this? Yes?
One thing I see is, I was thinking about doing the geometric mean, arithmetic mean.
Good. So that's a beautiful result, and we will get to the geometric mean, arithmetic mean. But when you just look at this equation, how would you describe this equation? Symmetric. So you should be seeing the word symmetry or symmetric, something beginning with a sim when you look at this. I've got A occurring twice in each factor, B twice, C twice on the left-hand side, and I have all possible pairs. I have 3 choose 2 pairs, all the way of choosing 2 elements. So one is there's no difference in the role of A, B, and C. So maybe some extreme point might be would be a good extreme point to check. Yes?
0, 0, 1, or 0, 1, 1.
Well, they all have to be greater than 0. So if it's symmetric, what might be an interesting point to check? I've got an infinitude of triples for A, B, and C. What might be a good triple to try? 1, 1, 1, or more generally AAA. So maybe try 1, 1, 1 or AAA. Now, one of my favorite concepts in mathematics is dimensional analysis. So I actually have a physics degree as well as a math degree. It is extremely useful at times. Later in the semester, I will prove the Pythagorean formula from a unit analysis perspective. How many of you have taken a chemistry class where you do factor labeling? Chemists are really good at this, and it's a very good way to make sure at the end of the day you have the right units. There was a $25 million whoopsie by NASA a couple of years ago where they had a probe that was landing on Mars, and all the systems were metric but one, which was in the English system. So when it was calculating how much thrust it needed for landing, it miscalculated and made a nice $25 million crater on the surface of the planet. Put in units. What units should we put in for A? I want to tell a story. What units would be for A? You can put in any units you want, but I mean, I have a default go-to unit or dimension. What would you like to say?
Apples?
Apples. Well, apples is more like a count.
Yeah.
So I want a physical, a unit you would see in a physics class or a chemistry class. What unit would I want? And it's got to be a unit where it would make sense to be adding and multiplying. So what would be a good unit? Meters. Right? Even though I think in the English system I would say meters and not feet. So this would be meters times meters times meters is meters times, ooh, this is interesting. It's meters cubed on both sides. Meters cubed versus meters cubed. So when we're looking at this problem, it's symmetric, and we notice that we have meters cubed on both sides. This is extremely useful. Now, if we put in 1, 1, 1, we get 2 times 2 times 2 is greater than or equal to 8. So it is a equality there. So maybe this could be the extreme place at 1, 1, 1. If we put in something else, if we put in 2, 1, 1, we would actually get the left-hand side is larger than the right-hand side. Then you would try maybe like 2, 1, 1. It seems reasonable that the minimum value of this might be occurring at the triple 1, 1, 1 or AAA. But because it's meters cubed versus meters cubed, we can make an additional assumption about this. Now, if you wanted to tell a story about this, maybe I have a box or something and I'm trying to calculate, maybe these are related to perimeters or whatnot. I don't know. Can I maybe come up with a story? I don't know. But I can assume something is true about A, B, and C.
Is it that the total outcome is like some like 1?
Yes, without loss of generality, what is A plus B plus C? 1. Because I can rescale A, B, and C by, say, a factor of R. And then I would rescale this by R cubed. I should be more careful as a Bostonian, but this is a good day to be a Bostonian, so I will definitely use the R. So we would have an R cubed on the left, and then we would have an R cubed on the right. And so it won't change things. So I could assume A plus B plus C equals 1. There is something else I could have assumed instead of A plus B plus C equals 1. What else could I have assumed? That's one idea. I could have assumed A plus B plus C equals 1. What else could I have assumed? Yeah, I could assume A times B times C equals 1. We get 1, not both. Which do you think is easier, to assume the sum is 1 or the product is 1? So one thing is, if I assume the product is 1, I get this is greater than or equal to 8. So again, I have not done this. This problem has not been prepared at home that much. I was a little bit busy last night. My gut feeling, though, is as much as I would like to take A, B, C equals 1, I don't think that's what I would choose. I think I would choose A plus B plus C equals 1 because of a result you have almost surely forgotten from Calc 3. So of all the results you've forgotten from Calc 3, which one do you think might be particularly appropriate right now? So imagine I have this function, and I could look at A plus B times B plus C times C plus A minus 8ABC, given A plus B plus C equals 1. What might I want to use from Calc 3? Lagrange multipliers. So we could use Lagrange multipliers with a constraint. And then which constraint do you think is better? A plus B plus C equals 1, and then when you take the derivatives, your gradient vector is going to be 1, 1, 1, or A, B, C equals 1. So for Lagrange multipliers, I think A plus B plus C equals 1. Again, I have not done this problem, but this is just how I would attack something like this. Yes?
What's Lagrange multiplier?
So Lagrange multipliers is if you want to maximize or minimize a function f subject to a constraint, you want the gradient of f to equal lambda times the gradient of g. And so we will definitely talk about Lagrange multipliers when we get to inequalities. This is just meant to be a quick introduction to the subject. I thought it might be just a fun way to start all the classes by just posting a problem. I'm happy to give you guys some books to look through, and if you see something that looks interesting, just throw it up. I don't care about being embarrassed live. I've got tenure. And just throw me a problem and just see how would I look at something new. And now this gives me a couple of things to try. So I have a bunch of go-to things. When I taught differential equations here in my first year, it was the spring semester. My daughter had just been born, and I taught differential equations as a father of a newborn. If the baby is crying, the baby can't tell you why, so you have a list of things to try. Does the baby want milk? Does the baby want to be held? Does the baby need a new diaper? Does the baby need to be burped? For differential equations, is the equation exact? Is it separable? Is it, you go through the list. You will have a list of things to try when you're looking at a problem like this. So whenever you see a problem, what can you try? Is there a symmetry? Is there a way to use symmetry to somehow attack the problem? Is there an induction going on? Induction is a great thing to try. And if so, what do I want to induct on? We're going to later learn about something called monoinvariance or invariance. It's a great way to attack the problem. Can I attach a natural quantity to this problem? Can I do some kind of dimensional analysis? And if I'm doing a dimensional analysis, that could give me an interesting perspective on how to look at things. Okay, so this is all I wanted to say about this problem. I strongly encourage you to try to finish the proof. There's multiple ways. The arithmetic mean, geometric mean is a great way to prove this. It is one of my favorite inequalities in all of mathematics. It is absolutely wonderful. We will see some great proofs of it later on. But right now, I don't really care about the answer. I care more about just the thought process as to how you would attack this. Okay, any questions on this? Okay. All right, so how many people here have not seen proofs by induction? All right, so has everyone seen proofs by induction? Okay. I need a volunteer, and that volunteer must have either a driver's license or a student ID. Okay, could you please take it out? All right, your name is Sean?
Yes.
Okay, I'm going to hold on to this for a little bit.
Okay.
So there, everyone is named Sean. Has anybody ever seen the Sean theorem? Okay. Out of curiosity, how many people here are named Sean? Only one person believes the Sean theorem. Interesting. All right, let me try to prove to you that the Sean theorem is true. Let's prove it by induction. So you said you all know induction, so let me do it by induction. So we do the base case first, right? In any, so wait, if I'm going to do induction, I should probably state what I'm inducting on, what the statement is. That might help. So let's let P of n be the statement in a group of n people, all have the same name. Okay? So base case. Is P1 true? If I have a group containing just one person, is everyone in that group sharing a name? Okay. I was going to say nothing up my sleeves, but right. Inductive step. So we assume Pn must show Pn plus 1 holds. Okay? So now, I believe all of these people are named Sean or whatnot, but for now, I will just give them the names 1, 2, 3, and then I'll just label them. And now let's look at, now I know in any group of n people by induction, they all have the same name. So what can you tell me about these n people? Same name. Wait, what can you tell me about these n people? Also have the same name. So I'm extremely glad that you chose to speak up, Sean, because you are the second person in that column. You're the second person in the second row. You are clearly the second person in this class. So I will observe the name of person number 2. I'm just making sure it doesn't have your ID, Sean. Okay, good. So this person is named Sean. So what must person 3 be named? Sean. So everyone must be named Sean. Sean, can you hand that to Sean? Thanks, Sean. Okay. So we're all named Sean. What's wrong? Yes, Sean.
It doesn't work when the base case is P1 and the base case P2.
Good. So what we're doing here is when I drew this picture assuming n was big, like 2. Maybe when n equals 1, this fails, because when n equals 1, this would be my first group of 1 person, this would be my second group of 1 person, and there'd be no common person. So we do have Pn implies Pn plus 1 if n is greater than or equal to 2. But P1 does not imply P2. I will not go through the exercise of asking a non-Sean to show me their ID. I will actually just check my ID. Yes, my name is Stephen. So the induction fails. People often draw induction like a ladder process, or a step, or a staircase. And we're missing the step from 1 to 2. And so everything breaks down. You may have, how many of you have ever seen this before? Okay, sometimes they do it by proving all horses have the same color. And then what's great is you can then prove anything in mathematics, because if that didn't hold, that would be a horse of a different color, which doesn't exist by the previous lemma. The other nice exercise, which I'll leave as a fun challenge problem for extra credit, is prove every integer is a perfect square. So you can prove every integer is a perfect square. Can somebody give me an integer that's not a perfect square? 3. Okay. So the theorem is obviously wrong. You can modify this false proof. And so again, it's going to be something where there's an inductive step missing. And so as a challenge, make another bad argument like this and prove that every integer is a perfect square. I think it's actually a really good exercise to try to come up with false proofs. This is not to confuse you, but to get a really good sense of what do you need to make the argument sound and solid. When I was taking physics, I had a phenomenal professor at Yale, and we used to believe that if he really wanted to, he could probably approximate and argue away special relativity. You've got to be careful. These things often seem reasonable, they seem reasonable, they seem reasonable. Where do you get at the end of the day? Okay, so what I want to do now is, we did not do power sums in this class yesterday, correct? Okay, so what I want to do, I know we did this in number theory, but I don't mind boring just one person. I'm going to talk a little bit about power sums, and I'm going to leave you with a challenge problem. If you are able to solve this problem, it can be done in groups, I will raise your grade an entire level for the semester. So if you have a B+, I'll move you up to an A+. There will obviously be a ceiling. If you have an A+, I'm not going to give you an A+++ or whatever that would be. Maximum of 1 full grade bump if you can solve the problem I'm going to pose. It may be a very easy problem. It may be a very hard problem. I have not spent too much time on this. I try to do this a lot. I try to have a problem, and I look at a simple case, and I prove that simple case for myself. And sometimes I tell people I've done it, sometimes I don't. I know enough so that I think that this is a reasonable project to give to students. And then I'll see what you can do with it. So I don't know how hard this problem is. It could be very easy. It could be impossible. But I'm willing to give you an entire grade bump if you can do it and you can work as a team. Okay? So power sums. So there's lots of ways. So the first is let's let Sn be 1 plus 2 plus n, the sum of the first n integers. The standard way of proving what this equals is to use induction. There's another nice trick, and this goes back to Gauss. The story is often told he was 5 years old, and the teacher was just having a really bad day and wanted to shut the brats up. So he said, add up the numbers from 1 to 100, and then just lean back to enjoy a couple of moments of peace.
We did talk about this.
Did we talk about this in this class?
Yeah. Did we?
No, we talked about that in number theory. This is why you've got to be very careful when you speak up. So there's a small overlap between this and number theory. Yep, no problem. So, but you can tell me if I tell the joke better this time. So he leaned back, expecting a couple of moments of rest, and Gauss immediately shouts out 5,050. So how is Gauss able to do this so quickly? Well, there's a reason he's Gauss. He wrote the numbers in reverse order. And then when you add up, you get twice Sn is n plus 1 is n plus 1. 2 plus n minus 1 is n plus 1. They all equal n plus 1. And how many times do we have n plus 1? N times. So you get twice Sn is n plus 1 n times. So Sn is n plus 1 over 2. You can also prove this by induction. It's much easier to prove things by induction if you know what you're supposed to prove. If you don't know what you're supposed to prove, it's much harder. Now, one thing that's nice about this is if you guess that there's supposed to be a formula, and that the formula depends on maybe the power we're raising things to. Maybe it's a polynomial. If it's a polynomial, you can figure out a polynomial by doing enough values. How many points determine a line? 2. How many points determine a quadratic? 3. So if you know that this is a quadratic, we would need to evaluate this for 3n, and then we could determine what the coefficients of the quadratic are. Now, if this is going to be a polynomial in n, what should the sum be when n equals 0? So then the polynomial must be a multiple of n. Ah, I've gotten the constant term. From calculus, as n gets very, very large, this is approximately equal from 1 to n of t dt. That's approximately t squared over 2. Oh, okay, that's t squared over 2 at 1 and n. And so this is approximately n squared over 2. So if we guess that it was a polynomial, if you guess a polynomial, it has to be of the form 1/2 n squared plus some constant times n. And if you want, you could then write that as, 1/2 n plus a. And then we would only need to choose one value of n to evaluate to figure this out, because we can use some calculus to guess. If we instead tried to sum the first powers, if we tried to sum the second powers or the third powers, we could go through the same argument again. If we had the third powers, we would have t cubed. We'd get t to the 4th over 4. So we would expect the sum of the fourth powers to be a polynomial of degree 5 over 5. We would expect a polynomial, if we had t to the 5th, we would have probably n to the 6th over 6. So you have a guess of what the leading term is. You have a guess of what the constant term is. If it's a polynomial, a couple of evaluations will suffice. This is not a proof that it's a polynomial. But if you're willing to make that assumption, you could then figure out what the coefficients are, and then once you have the coefficients, you could do the induction. So for example, let's say we want to do now Tn is 1 squared plus 2 squared plus n squared. And I claim that Tn is going to be n plus 1, 2n plus 1 over 6. And now we can prove this by induction. So let's check. When n equals 0, so if you want, I should really put a 0 squared here. I don't want to waste chalk. I need to save it for the large chessboards we'll do later in the semester. When n equals 0, good, it vanishes. Is the leading term 1/3? Yes, because I have a 2n cubed over 6. It's n cubed over 3. So this is a reasonable polynomial guess. what those middle coefficients are, that's harder. So proof. Base case. T1 is 1 squared, which is 1 times 1 plus 1, 2 times 1 plus 1 over 6. Yes. Okay. So now, inductive step. So we assume Pn, prove Pn plus 1. And so the way these inductive steps often work is you somehow have to find the expression. So typically what you would do is you would start looking at the statement Pn plus 1 and try to find Pn lurking in it. So we'd have 1 squared plus 2 squared plus n squared plus n plus 1 squared. Now what's particularly nice is we're trying to find Pn lurking in Pn plus 1. Here it's fairly obvious it's the first n terms. For some of the divisibility stuff, it's a little bit harder to find where it's lurking. This one is a little bit more straightforward. So by inductive assumption, what do we know this is? So this is going to be n plus 1, 2n plus 1 over 6 plus n plus 1 squared. So I'm going to write n plus 1 squared as n plus 1 times 6n plus 6 over 6. And I'm doing this just to try to make the algebra a little bit easier. And now, when I add, I'm going to have an n plus 1 over 6. And now when I add, I'll have 2n squared plus n plus 6n plus 6. Now for the statement Pn plus 1, it should be n plus 1, n plus 2, 2n plus 1 plus 1, so that should be 2n plus 3. So now when I just do some algebra, I have n plus 1. This is going to be 2n plus 7n plus 6. So I'm going to get 2n plus 3, 2n plus 2. I'm sorry, n plus 2. So I think n plus 2, 2n plus 3 over 6. And again, this is where I can use the fact that I know what my target is to help me with the algebra. And then this part I can just write as 2n plus 1 plus 1. The second write is n plus 1 plus 1. And that proves the claim. OK. Everybody comfortable with doing this? If I asked you to do cubes, if I give you the formula, it's just algebra. And in fact, what you could do is if you're not sure if this factors into this, what you do is you take this and then you subtract off what you think it's supposed to be, and then you just cross multiply, expand, simplify until you get 0. So at this point, there's really no longer any challenge. All right. So you ready for the opportunity? So we've got the power sums of n and n squared. I want to get the general power sum using just those two facts. I do not have an elementary proof of the sum of squares. I'd love to see an elementary proof. What do you think the next one we should look at after the sum of the first powers and the second powers? The third powers. All right. So I'm going to get the third powers elementarily, and it's going to allow me to review some nice techniques. So consider un is 1 cubed plus 2 cubed plus n cubed. We want to figure out what this equals. OK. I'm going to start with what I know, and I'm going to explore. So let's look at the sum k. K goes from 1 to n squared. Do we know what the sum of k is? Yeah, what would that be? Not k. Close. We're summing k goes from 1 to n. So it's good. So it's n plus 1 over 2, but we square everything because we're squaring it over 4. And this is going to be the sum k goes from 1 to n of k times the sum L goes from 1 to n of L. I can't use the same dummy variable twice. This is one of the most common mistakes people make in calc or in summations, is they use the same dummy variable twice. So now I want to expand this. So everybody's comfortable with FOIL, first, outside, inside, last. This is now FOIL on drugs because we now have n terms, so you have a lot of interior terms. So there's two possibilities. When I multiply things out, I could have L equals K, or I could have L and K being different values. If they're different values, once I'll have the smaller here and the larger here, and once I'll have the larger here and the smaller here. So when I cross multiply, I might as well assume that the first one is always smaller than the second, and then double that, and then add back all the ones where they're the same. And so if I do that, I get n squared, n plus 1 squared over 4 is equal to the sum, k goes from 1 to n, of k squared, plus twice the sum, k goes from something to n, and the sum L goes from something to something, of k times L. Now we're assuming k is less than L, so what's the range for L?
Plus 1 to n.
I'm sorry?
K plus 1 to n.
So,
This, not k plus 1, but
so if I'm running it like this, it's really bad to have k be the smaller one, right? I would want to do the L sum outside if I'm going to have k be the smaller one. So, and you've got to be very careful about how you put the indices, because if I'm summing L, if L is bounded in terms of k, I've got to be very careful. So here, I want k going from what to what? 1 to L minus 1. And then L will go from what to what?
1 to
Not 1, 2. L has to be greater than k.
yeah. I guess if you did 1, then the second side just wouldn't matter.
Right. It would then absorb this. And I want to split this off. All right, so now let's do the sum. Well, the nice thing is I can do the k sum, right? And so this is going to be the sum, k goes from 1 to n of k squared, plus twice the sum, L goes from 2 to n. And now when I do the k sum, I go up to L minus 1. So we get L minus 1 times L, which is L minus 1 plus 1 over 2. And then I have to multiply by this L as well, so I have an L squared. So now what do I get? Well, the 2's cancel, and I'll get a sum, k goes from 1 to n of k squared, plus a sum. Now, could I move my L sum down to 1? Yeah, I've got an L minus 1. If I adjust the L sum to go from 1, it's not going to change anything. So I have L goes from 1 to n of L cubed minus the sum, L goes from 1 to n of L squared. Now what's really nice is we don't actually need the value of the sum of k squared, because it perfectly cancels with this. So these drop out, and the sum of the cubes is just n squared, n plus 1 squared, over 4.
How did you adjust the index?
So we have this factor L minus 1 times L squared. If I put in L equals 1,
Made it L cubed, so
right. And then, so the first thing is I move L down to 1 from 2, because that's adding 0, which I can do. And then I expand this out as L cubed minus L squared. Here's the L cubed piece, here's the L squared piece. I want to make sure that everything's good. You still seem a little hesitant.
yeah. So you moved it down from 2 to 1.
Be-
Wouldn't it need to be L minus 1 cubed?
No. I've got this sum, and I go through all values of L. I put L equals 2, L equals 3, L equals 4. What happens if I substitute L equals 1 into this expression? I get 1 minus 1 times 1 squared, which is just 0. So I can move the sum down to 0. Could I move down to 1? Could I move the sum all the way down to 0 if I wanted? Yeah, because I've got the L squared here. So if I wanted to start the sum at 0, I could have done that as well. Could I move the sum all the way down to negative 1? No, because then I would be adding -2 times -1 squared. I'd be adding something. So what's nice is when the dust settles, we now have a formula for the sum of cubes. And we get that this is going to be n squared, n plus 1 squared over 4. We might also get a conjecture that maybe these higher sums are related to squares of lower sums. Completely false. Is there a geometric reason behind this? This seems really strange that something like this is going on. So my question is, can you use the fact that we know what the sum of the first powers and the sum of the squares are to get everything, to get the sum of the fourth powers, fifth powers, sixth powers, seventh powers? Can you keep doing this trick? And can you do it in a good way? If my life depended on it, I'm sure I could do it for the 2017th power. But if I don't have a general approach, it would be painful. I want a good, clean, elegant solution. There's no grade bump if it's not nice. You know, if you have to just roll up your sleeves and chug away, chug away, chug away, that's not going to work. I want to get the general pth power very cleanly in terms of just these two inputs. So what you can do is you can assume maybe you have shapes of the lower ones and then just keep marching down. We know, we know, we know. Okay. Any questions on the power sums? So this is one of the most common things that is done with induction. Okay. All right, everybody's good? Okay. And then I think I've assigned, 2 induction problems for homework for Friday. And a big part is, can you figure out what the formula is? And then once you figure out what the formula is, can you figure out how to sniff things in? All right, so what I want to do now is I want to state briefly the cookie problem. So I usually cover this in my probability class. I want to do just a little bit for you, and I want you to try to write a little computer code to sniff out the answer. I will probably have Wednesday's class be a computer programming tutorial because I really want you to have basic programming skills on the level of for loops and if statements. There's a lot you can do with stuff like that. Then if you're really good, you can try to write code efficiently. And that's wonderful if you can, but the first thing is, can you write code well enough to just investigate the problem? All right, how many of you are considering a career in graduate school? All right, I have to warn you a little bit about what it's like. When I was a postdoc at Brown, there was a free food email list for grad students, where people would send out an announcement, there is a talk today at 4 o'clock, followed by this type of food. And the graduates would go, I can listen to that for pizza, or crackers? No, I'm not going to listen to that for crackers. Grad students get very hungry. The pay is a little bit better now, but free food is useful. And so what I'm going to do here is I'm going to assume we have P people. I often do graduate students so they're hungry. I will assume that the people are distinguishable. Okay? Now, if this is an engineering graduate program, that may not be the case. If you have a lab science where everybody's a peon, it may not be the case. But we'll assume this is a good graduate program like pure math, and the grad students are distinguishable. I assume we have C cookies. And I will assume the cookies are not distinguishable. So here, distinguishable. And here, they're the same. And so my question is, how many ways can we divide C cookies among P people? So is there a difference between my getting all the cookies and Sean getting all the cookies? Yes. Okay, so how many ways to divide C cookies among P people? So for example, maybe P equals 5 and C equals 10. Can someone give me a bad way to attack this problem? I don't care how bad it is. Great! So what we could do is we could do A, B, C, D, E. We will assume that the grad students have very unoriginal names, but this is good because we can quickly look down and keep track. You don't want to have strange names. Or if you want to have names that are interesting, you know, maybe Ariel, Belle, Cinderella. What am I doing? Trying to do Disney princesses. So you would choose a name where the letters are going in order, so you can quickly look down. So one possibility is we could go 10, 0, 0, 0, 0, 0, 10, 0, 0, 0. And there are some tricks you can do to fill in the table a little bit faster. I'll leave that for you to figure it out. So what I'd like you to do for Wednesday is try a couple of values of C and P and see if you can guess the formula. Okay? If you already know the formula, then you're in really good shape for this, and do not share it with anyone in the class. Do not try to look up the formula. You can do this by brute force, or you can write a computer program. Can you sniff out the answer? And if you can sniff out the answer, the problem becomes a lot easier. If I tell you what the answer is screaming at you how you should prove it. But if you don't see the answer, it's much harder to think how to attack this. So gather some data. I maintain a math riddles page, which is often in the top 10 in the world when you Google math riddles. This was the first riddle that started the page. I was a graduate student, and one of the undergrads brought this to me and wanted to know how to do it. I love this problem. There's a lot of great mathematics behind this. I've used this idea in several of my research papers. It's a phenomenal idea how to look at this problem. If you don't instinctively see how to look at it, gather some data and use that data to figure out how you might attack it. Okay? So everyone is clear on the problem. So the answer is going to somehow depend on C and P, and I want to see if you can sniff out what that dependence is for Wednesday. We may not talk too much about it on Wednesday, but maybe we'll use that as one of the things we program together in class, as to how would you investigate this. Once you see a pattern, can you figure out what it is? We've talked about the online encyclopedia of integer sequences. Have we mentioned that? So if you have a couple of values, maybe you can put this in and somehow get an idea. Okay. Any other questions on the cookie problem? Trying to see how much time we have left. Okay, we've got 5 minutes left. So there's so much wonderful stuff to do. So let's do a tiling problem. So we have 2x1 blocks. And the goal is to tile a 2x(n) grid. Count the ways. So how many ways can we tile a 2x(n) grid? What's the first thing you should do when you're trying to figure this out?
Set some value for n.
Yeah, set some value for n. What's the first value of n we should do? So when n equals 1, how many ways? One way, right? There's one way. When n equals 2, how many ways? 2 ways. So we can do it this way, like this, or we can do it this way. When n equals 3, how many ways? 3 ways. So we could do it like this, all up. We could do it this way. Is this right? Yeah, this is probably where, and then we could also have done it, not the greatest picture, but this way. Oh, 1, 2, 3. What would you guess for n equals 4? 4 ways. So the question is, what's the best way to go? So let me draw a little bit better picture here. So 1, 2. So your one possibility is we put the first piece up. And if we put the first piece up, then how many choices do we have? 2. But we can view that as we've reduced it to the previous level. So if we put the first piece up, then the number of solutions is the previous level. If we put the first piece horizontally, then we've got to be horizontal above that, and what have we reduced it to? The last two. So let's do this, but let's set up a relation. So let's let Tn be the number of tilings of the 2 by n. We know T1 is 1, T2 is 2, T3 is 3, and Tn plus 1 is Tn plus Tn minus 1 if n is greater than or equal to 2. Have you seen this before? So this is the Fibonacci's. So the question is just how rigorously do we want to prove that these are the Fibonacci numbers? Well, if you define the Fibonacci numbers this way, then we're done. Now we could ask questions about how rapidly do the Fibonacci's grow. What can you say about Tn? And there's a lot of beautiful mathematics here. There's a lot of wonderful closed form expressions for the Fibonacci numbers. There's a lot of theories to how would you solve difference equations like this. And so later in the semester, we will talk about how you solve a difference equation like this. What I want to do is I want to end today with rough ballpark estimates. Okay. And again, I apologize a little bit if we're jumping all over topics, but in some sense that's the whole purpose of this class. Is when we see something, if there's an interesting thing, let's run with this. So the Fibonacci numbers have an immense number of interesting properties. So we have this relationship, Tn plus 1 is Tn plus Tn minus 1. And I want to understand how rapidly the Fibonacci numbers are growing. Can anybody think of a way to bound how fast the Fibonacci numbers are growing? Tn plus 1 is less than or equal to what? 2Tn. And it would be greater than or equal to? So basically, every time you increase n, you would most double the Fibonacci number. So this part over here is going to imply that Tn is growing slower than 2 to the n. Now we have to be careful in terms of have we shifted the Fibonacci definition, because often the Fibonacci's go 1, 1, 2, 3, and we're going 1, 2, 3. I'm not worrying about that. But every time we increase n, we at most double. If you go in the other way, every time we increase n twice, we double. So what should the growth rate be here? It takes two iterations to double. 2 to the n over 2, or square root of 2 to the n. And then if we do two things, we get root 2 times root 2 is 2. So we expect Tn to be growing somewhere between 2 to the n and root 2 to the n. And this sets us up for one of my favorite methods of mathematics, the method of divine inspiration. So the method of divine inspiration is you solve a problem by writing down the solution. When you're divinely inspired, it works really well. What this is telling us is Tn is growing exponentially fast. We don't know exactly what the rate is. So let's guess Tn is r to the n for some r. And then you would get what's called the characteristic polynomial. How many of you have seen this before to solve the Fibonacci's? Raise your hand if you've not seen the characteristic approach before. Okay, I don't want to rush through this. So I'll stop here. We'll definitely do more on this later, but this will lead to Benet's formula. This will lead to a lot of great mathematics. The idea is this is not an unreasonable guess for the solution because we see that it's growing exponentially fast. And it turns out if r to the n solves this equation, would 5 times r to the n solve this equation? Yeah, the equation is linear. This is very similar. Oh, this is similar to what we did at the start of the class. Oh, maybe it was useful we looked at that. If you had two different roots, r1 and r2, that worked, r1 to the n plus r2 to the n would also work. And eventually, you'll try Tn is c1 r1 to the n plus C2 R2 to the n, where R1, R2 are roots of the characteristic polynomial, which will be R squared minus R minus 1 equals 0. So if you want a fun exercise, try to use this to write down and get to Benet's formula. All right, so this is basically going to be as much as I want to lecture in class on induction. I'll give you some induction problems to do. We will spend Friday doing coding. We'll try to use the cookie problem as a motivation for the code we're going to write and see if we can sniff out formulas. That's really going to be one of the themes of the class, is given a problem, how do you go about trying to get a sense of the shape of the answer? Okay.